All right. Yeah, thank you for the introduction, and thank you for all the organizers. It's always a pleasure to be here at Types. So I'm going to be talking about the only thing I've been able to think about for the past whole year, which was my PhD, which is finally done, and now I can live my life. And so this is a presentation of, in particular, chapter 4. So if you want any of the kind of gory details, then you can read chapters 0 through 3. Yeah. Okay, so this is connected. The last question on Fernando's talk was perfect segue into this, and so yeah, we can kind of just continue this conversation. So as is well known, Martin-Löf type theory provides a kind of synthetic theory of groupoids. So we have so in the when I say synthetic groupoids, I mean that the terms of a given type are like the objects of a groupoid, and then the identity types provide us with the morphisms of the groupoid. So we have the identity morphism, which is given by Reffel, and we have composition of morphisms. So if I have P from T to T prime and Q from T prime to T double prime, then I can compose them. And so that's what gives this kind of a synthetic category structure. And this is defined by the path induction rule, the J rule, or the Hom elimination. And we also get that we can invert these morphisms. So given P from T to T prime, I can get the P inverse from T prime to T. And that's also defined by path induction. And so this is a familiar story, and of course, homotopy type theory has gone wild with this idea and done infinity groupoids and all that. But like Fernando, the question I want to ask is, how can we get a synthetic category theory? How can we come up with types that have these kind of Hom types on them that are still we still have the identity morphisms. Yay, we like identity morphisms. And we still have composition of morphisms. That's good, but no inverses. We don't want our types to be groupoids necessarily. We want them to be categories. So we don't want to be able to do this inverse operation on morphisms. And this is kind of a big challenge because if you notice that like I said, both the composition and the inverse are proved by this J rule, by path induction. And so they're not axioms, they're theorems. And so it's a real challenge. I would say it's the kind of fundamental challenge of directed type theory, at least if you want to have your Hom types introduced by judgment rules like this, is how do you weaken the J rule so it can't prove symmetry, but it can prove transitivity. It's a very subtle thing. And so the route that and get synthetic categories that aren't necessarily synthetic groupoids. And so the route that Page North goes down, and that Fernando was talking about, and that I'm also following, is to use the kind of polarity annotations. Fernando wrote op, I'm writing the superscript minus. And so what it is, we have types, and we annotate them with a minus to indicate that they're contravariant. So for every type A, there's another type A minus, which is the kind of contravariant, the evil version of A. And the way to think of this is that if our types are supposed to be categories, then A minus is just the opposite category of A. And so these annotations allow us, so we can put these annotations on the Hom types. And so we can say that if T is A minus and T prime is in A, then we can form this Hom type, Hom T T prime. And this is ultimately going to be what prevents symmetry from being provable, but allows the transitivity of the composition to go through. And so and so this was all and this all has semantics in the category model, just as Fernando was talking about. Yeah.
So say types are categories for the Hom case and
The objects are the terms of that, and then the morphisms are the terms of the Hom types. Okay. So where I'm differing from the way that Page and Fernando were doing this is instead of using core types or instead of using these kind of two-sided vibrations, instead what we can do is we can look at just closed terms. And actually, I mean something more general than closed terms. It's not necessarily just the empty context. Actually, you can do this in any groupoid context in the category model. But I'll just use the term closed here because it's kind of a nice word. And so what it turns out is that if you have a closed term that in this sense, then you can coerce it back and forth between A minus and A. So you can't do this in general. You can't go back and forth between A minus and A. They have, if you look at their semantics, they're very different. And this is why Fernando mentioned Page need to introduce these kind of core operations to be able, to have terms that you could use as negatively and positively. But here instead we're doing closed terms. And so we get this coercion operation. And the intuition here is that a category and its opposite have the same objects. So it'd be kind of weird if this wasn't the case, because A and A minus are supposed to have the same terms, the same objects. So the key point is that we cannot, in general, negate open terms, and so this is also a key part. So if I have a term x here of A minus, I can't negate it to get x and A because it's not a closed term; it's an open term. And so that's a key rule here. And so with this negation operation, then we can state the Hom introduction. So we can state REFL, and that allows us to have T in both the negative and the positive position. Just we coerce it into the positive position. So this is the kind of distinctive feature of this approach to directed type theory is making use of these coercions to solve this kind of divariance of REFL problem.
Would it make difference between A minus T?
Sorry?
You did A minus T, would it make difference?
No, it wouldn't. I mean, given that A minus minus is A and minus minus T is T, so yeah, it was just an arbitrary choice to phrase it this way. Yeah. Okay, and so this gives us REFL. So we just have to kind of add a few annotations here to note where the variances are. So this gives us REFL, right? So we have identity morphisms, and we have a principle of Hom elimination of path induction. Oh yes. It's not like I said, it's not just the empty context. It's there's this classic groupoid context where this works. So you have to kind of work internally to a groupoid context. So everything I'm doing here is kind of informally working in an ambient groupoid context. And so we get this directed path induction principle that says that if I have any term T, and if I have a type M depending on a coslice under T, then in order to inhabit M for an arbitrary coslice x prime and u, then it suffices to just inhabit it for x prime is minus T and u is REFL T. And so this is the kind of usual idea of how path induction works. And with this, so the kind of way to think of this is that REFL is the kind of universal coslice under T. And so this solves the kind of fundamental problem of directed type theory. So we can still do the proof of composition. So this all abides by the rules by polarity rules that I've set down. So that's fine. But if we try to do the symmetry proof, then we would need to put minuses here and here in order for this to even be well formed. And if we try to keep the same path induction that we had to try to define this symmetry term, we've broken the rules here because we've negated an open term. And so that's how we defeat the symmetry proof and kind of thread this needle of having composition, but not having inverses in general. So, right. And indeed, this is all given semantics in the category model, and so we can do an independence proof to show that there's no proof of symmetry. So this one in particular fails, but there's no way to prove in general that symmetry holds. So these are this is genuinely directed type theory. These are synthetic categories, not synthetic groupoids in general. Okay, so for the last bit, I want to make an observation. So I said we want to do synthetic category theory. And so category theory is really concerned with universal mapping properties. That's the kind of bread and butter of category theory. Whereas type theory is usually you want to introduce a type theoretic construct with a principle of induction. And so the idea of this style of synthetic category theory is that we should make our universal mapping properties to be principles of induction. And so we already did that a minute ago in that this principle of co-slice path induction. And by the way, when I say that there's co-slice path induction, that implies that there's a slice path induction, and indeed there is. It's just the kind of opposite, as you might imagine. But here, I've taken a categorical property. The identimorphisms are the kind of universal or the initial co-slice, and I made it into a principle of induction. We've already done that here. And so the idea is to take this idea and run with it, and phrase all of our category theoretic ideas as principles of induction. So here's an example, is coproducts. So I have two objects, S and T. I put them as A minus, but since they're closed, it doesn't really matter. And a coproduct of S and T, well, it should consist of an object, Q, and morphisms, iota 1 and iota 2. I think I drew them backwards. Yes. Sorry, that should be iota 1. Yeah, iota 1 and iota 2 go into Q because this is a coproduct. And then the principle of induction is this, that if I have an arbitrary cocone, if I have a type depending on an arbitrary cocone, then in order to inhabit that type for an arbitrary cocone, it suffices to inhabit it just for the initial one by the coproduct. And so here we've written the principle, the universal mapping property of the coproduct as a principle of induction. And from this, you can derive the usual one. So you can derive, given this cocone, you can derive a map from Q to X prime, and you can prove internally by path induction. So you define that by path induction. You prove internally by path induction that the triangles commute. You prove internally that that's the only morphism making the triangles commute. And so you recover the usual notion of the universal mapping property of the coproduct, but now we have this in this nice inductive style. And so we can go a little bit further. In this calculus we have functors, or we have function types which serve as synthetic functors. So a function f from A to B is a functor from A to B, and so we can do all the nice functor things. We can define the identity functor. This is really hard to do in the category model semantics because of all these annoying polarities, and so that's what these groupoid contexts are really good for, is kind of making all the polarity go away so we can write normal stuff like lambda x dot x. And we can define the morphism part of functions as functors. And so these are synthetic functors in that any function you could possibly write down automatically comes equipped with a morphism part. It's functorial and blah, blah, blah. And this is all, of course, just defined by path induction. So if f little f is ruffled, then map f little ruffle is just ruffled. And we also have natural transformations, which are just the Hom types between functions. And so we can define, again, by co-slice path induction what their different components are. So if I have f and g, and I have alpha from f to g, and I have a term t, then I can get the component of alpha at t, which basically goes from f of t to g of t, just with all the annotations I need. And we can define the notion of adjoints. So So an adjoint is for a functor u is something with this universal property. I'm running out of time, so I'll kind of just zoom through it, but it's exactly what you'd expect. It's that, yeah, we just phrase the universal property of an adjoint using as a principle of induction. So I'll wrap it up there. There's all kinds of different stuff that has already been done in this kind of category theory, and there's still a bunch of stuff that needs to be done and more extensions to the logic that need to be done. But yeah, you can read all about that. There's some citations, and so thank you for your attention.